To the 2021 BHT lecture series, 21 because it was postponed from last year because of as you well know, problems with the pandemic. But I believe they are going to have a 2022 one. I don't know anything about it yet. It'll be probably later in the year, around October-ish time. June, isn't it? That's already been planned. That's really good. This is actually the last lecture in the series. Heloise has been going to a number of venues around New Zealand, and so we're lucky to be able to be here in person, and we're also live streaming. Unfortunately, our live streaming technician's daughter came down with tested positive for COVID-19, so he's unable to be here. So he's actually handling the broadcast to YouTube remotely. Anyway, if you don't know what BHT is all about, it stands for Beatrice Hill Tinsley. She was a very accomplished astrophysicist. She was basically raised in New Zealand. I think she might have been born in the UK, but lived most of her young life here. Became a graduate in the astrophysics field and eventually took up a professorship at Yale University. And she's very well known for doing a lot of pioneering work in the evolution of galaxies. But unfortunately, she died at a young age, only 40, from melanoma. So there's been a number of awards and other events that have been established in her honour, and this lecture series is basically to honour her. We have our international guest speaker this evening, Dr Heloise Stevence, who's also an astrophysicist. She's been at the University of Auckland for how many years? 3 years? Nearly three. Yeah, unfortunately we're losing her soon back to the UK, but she's going to bring us up to date on the deadly dance of black holes and neutron stars. So thanks very much for agreeing to do this lecture series for us. Thank you very much.
Tēnā koutou, tēnei te mihi ki a koutou, ngā mana whenua o te wahine, ko Pirene tō maunga, no wiwi a hao, ko Heloise tō ingoa. Greetings everyone, my name is Heloise, thanks for the introduction. I am French, originally from the Pyrenees. I'm also going to do a Jacinda and remove my mask because otherwise I might pass out. So yeah, if you get confused at any point by my accent, it's the French coming out. Sorry about that. I'm very fortunate that my travels have brought me here to Aotearoa, and so I begin every single one of these talks by acknowledging the people's sovereignty to this land, and every single one of you for coming here tonight and choosing to spend your time listening to me talk about black holes and neutron stars, you absolute nerds. So we're going to talk about what happens when black holes and neutron stars collide. I'm also going to start my timer so we're not here for an hour and a half. We're going to talk about how black holes and neutron stars even arise, how they are born in the universe, what happens when they come together, and how we can observe and see these phenomena and what we can actually learn from them. But before we go into that, we need to go back to fundamentals and ask ourselves, what's a black hole and what is a neutron star? Now, a black hole, you may have heard, is a singularity in the fabric of space-time. It's a lovely word salad, but not necessarily that meaningful if it's not been explained properly. Singularity, anytime you hear a physicist, an astronomer say, or mathematician say singularity, I'm using the mouse occasionally because the people online can't see my fancy dandy green laser pointer, matches the hair. We like that. Singularity just means that mass breaks in that particular region of time or space. It's not that it's necessarily a single point, it's that the mass that we use to understand the world, to explain the physics, breaks down. Now, the fabric of space-time is gravity with a little bit of spice. Gravity in the Newtonian sense, in the classical sense of the word, is very basic. Two objects that have a mass will attract each other. In general relativity, it's a little bit different. And once again, I'm going to use the mass. I'm going to get out of shot. Sorry about that. Because we're going to use this representation where a mass causes a little divot, a little warping, little funnel, if you will, in the fabric of space-time. Now, the fabric of space-time is a four-dimensional thing. Very difficult to picture four-dimensional things, so we're not going to try to do that tonight. It's too late for that. We're going to use a two-dimensional visualization, a pretty classic way of seeing things. Now, orbits of stars, of planets around stars, are very well explained, very intuitively explained by that weird diagram, actually, because essentially something that comes towards a very massive object will then fall into the funnel. And if it's coming out quickly at an angle, it's going to roll around the lip of that funnel. The way I like to picture it and explain it is by maybe jogging your memory, thinking about those funnels you see at the entrance of museums sometimes, you know, that trying to encourage you to spend your change that nobody has anymore. But back in the day, when people had change, they would roll coins at speed down a little ramp around that funnel. And if you do it right, if you give it enough speed, it can rotate around that funnel without falling in quite successfully. But if you don't give it enough speed, it's just going to fall right in. Now, same idea for space-time and stars and things that have a mass. The more mass in the smaller amount of space, the higher the density, the deeper the funnel, and that's it. But what happens if the funnel is so deep that the speed you need to stay in orbit is faster than the speed of light? Well, that is where physics breaks. That is where we have a problem, and that is where we have a black hole. Black holes do basically what they say on the tin. They are black because even light cannot escape them, does not move fast enough to escape them. So all black holes are the densest objects in the universe, and they're typically more than 3 or 5 times the mass of the sun. That is nothing to do with a fundamental law of physics and everything to do with how they're born, which we'll go back to later in the talk. If you really wanted to, you could take all of the mass in the planet Earth and turn it to a black hole. You would just have to condense it down to an object the size of a marble, about an inch across. So really extreme stuff. Now we're going to move on to our neutron stars, our second really dense objects. And like the black holes, they basically do what they say on the tin. They're made of neutrons. A neutron, let's just recap, is a subatomic particle. It's the little N, the white ball right here in the atomic nucleus. Neutrons are neutral, hence their name. They have 0 charge. The other particle in the atomic nucleus is a proton, positive charge. It's the red thing over here. And to complete an atom, you need a bunch of electrons flying around the blue dot there that has a negative charge. If your electrons and your protons are squished together, which only happens in very crazy environments, like the neutron star, then they form neutrons. And that's why we have effectively a big ball of neutrons, the size of a city, roughly, about 10 kilometers across. This ball right here is about 10 kilometers across, but it packs a punch between 1 and 2.5, 3 times the mass of the sun, roughly. Now that's really hard to picture, that much mass in such a small space. So once again, I'm going to try and give you a little analogy. If one of your red blood cells, just one, was made of neutron star material, it would weigh about as much as Donald Trump. Which you've got to admit, pretty dense, pretty dense. Thank you very much. 12 talks have given that joke 12 times, but it's fine. It works every time. Right, so these are the second densest objects in the universe, but these still shine. They're not dense enough to trap the light. They are still very bright. So how do you make things like that? How do you make such dense, such extreme objects when most of the universe, let's be frank, is a whole load of nothing? It's a whole load of empty space, wisps of gas and dust across very vast distances. So how do you go from these clouds of vague gas and dust to things like that? Well, a long time ago in a galaxy, okay, I'm going to start. There's going to be only a few nerd jokes, I promise. No, like most things in the universe, if you're wondering where it came from, it was probably a star, right? And this is the part of the talk where I usually ask a question to the audience. We always love these, right? And pre-COVID times, I would actually go and harass people into the audience to answer the question, what's a star? But since we're going to be COVID conscious, I would like you to harass yourselves and actually raise your hand and answer my question. What's a star? Yes. Oh, we're going to let the kid do it. Oh, come on. Yes.
Star is like a big lump of gas.
It is a big lump of gas. Your answer? Big lump of gas times 2. Anything else? Big lump of gas times 3? Yeah.
The heat comes from thermonuclear reaction.
We've got thermonuclear reactions somewhere that make it really hot. Anything else? What's a star made of?
Hydrogen.
Hydrogen. We've got a lot of hydrogen. Right. So we've got a lot of basic components here. Love it. What else?
Helium is some stars are oxygen. There's lots of layers.
There's lots of layers indeed. We love it. Hydrogen and helium are the main components of stars. It's always the kid that shows up to be a doctor like, aha, I will do it if you don't have the I'm not going to say that word to do it. So we've got a lot of gas that is indeed very hot and very shiny. And that gas is mostly hydrogen, about 75%, about 25% of helium, and about 2% of everything else, which in astronomy we call metals. The periodic table of elements in astronomy, very simple, very simple. Hydrogen, helium, metals. It's like a holiday for chemists. We love it. Now that's just the ingredients, but in order to get the full recipe, we need to understand the forces that act on these ingredients. And there are 2 key forces in our stars. First of all, we have gravity. It's a lot of mass in a relatively small amount of space, so all of that stuff is going to be pulled towards the center of the star. And if there's nothing to stop it, it's just going to keep collapsing. So we need something else to balance gravity, because we want our star to live for millions, billions, trillions of years. And that force is going to be pressure. That pressure that's going to be exerted from the center of the star by mostly nuclear reactions, right? So nuclear reactions, pretty basic. It's not true. They can be very complicated, but we don't have time for this. Nuclear reactions in stars essentially is taking a bunch of light elements, banging them together to make something heavier and getting a load of energy out of it. In this case, we have 3 helium. You bang them together, you get a carbon and a load of energy. And that energy is going to do a bunch of things. First of all, it's going to heat up the environment. And heat is just particles moving quickly, moving faster. And if they move faster, they bang into their friends, into their neighbors faster, creating that pressure that we need. The other thing it's going to do is create a bunch of photons, a bunch of light, which is going to make our star shine, which is one of the key characteristics of the stars. Now for 90%, oh no, I forgot, sorry, science. Now the balance between gravity and nuclear fusion is therefore essential to the life of our star, to its equilibrium, to it being stable. And the disruption of that balance is essential to its death. For 90% of the life of our star, it's just going to be burning hydrogen into helium in the core, the middle. And that's going to be pretty boring most of the time. So not much happens. It gets interesting when the hydrogen in the core runs out and other things have to happen, the last 10% of the life of our star. And in order to understand what these last 10% are going to look like, we're going to split our stars into 2 categories, the low mass stars and the high mass stars. The low mass stars, less than 8 times the mass of the sun, the high mass stars, more than 8 times the mass of the sun. It might seem arbitrary, but stars, their death in particular, and the rest of their evolution is very well determined by their initial mass. It's one of the key factors that determines what their life is going to look like. You may not have seen the separation before, but you know stars in both categories. The low mass stars, our sun, obviously by definition, is a low mass star and makes the beautiful sunsets. Now the high mass stars, you know a load of them as well, because the vast majority of stars you can see with your eyes in the night sky are actually high mass stars. For example, the stars in Tautology and the rest of Orion, which, by the way, notice it's the right way around. Despite being from the northern hemisphere. So all these stars, high mass stars. And the reason that most of the stars that you can see with your eyes in the night sky are high mass is not because they're more common. On the contrary, for every high mass star, you've got 50 to 100 stars like the sun. The reason you see most of the stars you see in the night sky are high mass is because they're much more massive, they're much brighter, therefore you can see them from further away, and that's why they dominate what you can see. They're actually the ones we're going to focus on today. And in order to understand the difference between the low mass and the high mass, we need to look at a very ugly plot from the mid-20th century. It's a classic physics lecture thing to show a plot like this. I would lose my PhD if I didn't show you one of those. But it's actually very useful. Don't panic. I'm going to show you what's in it. And in order for the people on the internet to understand, I'm going to actually use the mouse. So this plot shows you different elements in order of how light to how heavy they are. So we've got hydrogen over here, very light, uranium, lead, plutonium over there, very heavy. And on the y-axis, we've got the average binding energy per nucleon, which is a bit of a word salad, but essentially it tells you how much energy is contained in the protons and the neutrons hugging each other very tight in the atomic nucleus. And in order to understand how much energy you release in a reaction inside the star, you just need to look at where you began and where you ended up. So for hydrogen, you start here. Then you make helium with your hydrogen, you end up here. So you go up a lot. That's the biggest difference in the entire plot. And I'm not drunk, by the way. The reason the mouse is doing some weird things is because there's a lot of stuff on that desk that I didn't put there. So I'm doing my best. So hydrogen to helium, big difference. You're going up that curve, you're releasing energy. Once you run out of hydrogen, you start burning helium into carbon, you release a lot less energy, it's less effective. That's why that part of the life of the star only lasts 10% of its life, because it's just not as good at doing it. Low mass stars are going to stop at carbon, because the heavier the element, the more gravity you need to push the elements into each other, right? With the high mass stars, you can go all the way up to iron. And that's a problem, because it's at the tippy top of the curve. And in order to release energy, you need to go up on that curve. But with iron, whichever way you go, whether you make heavier things, going down, or you make lighter things, also going down, you're not releasing energy, which means that gravity wins and the core collapses. In about a quarter of a second, the equivalent of 1 to 1.5 times the mass of the sun is going to collapse into an object about 10 kilometers across. The pressure is going to be so high that electrons and protons are going to merge into neutrons. That's our proton-neutron star. That's our baby neutron star. The vast majority of stars, of high mass stars, that's what's going to happen. The rest of the stars also going to start collapsing, not quite as quickly. And then because that neutron star is so dense and so solid, the outer layers of the star is going to bounce off, create a shock wave and a big explosion, which we call a supernova explosion. And if you wait just a few hundred years and put, say, 4 telescopes out into space, you can get pictures like these. They're my favorite nebulae. We have Cassiopeia and the Crab Nebula. And what's amazing about these so-called supernova remnants is that you can actually see the neutron star in the middle. In Cassiopeia, the neutron star is here. That is the blue dot in there, right there. The entrails of the star that exploded about 350, 400 years ago. It's mostly the yellow stuff over there. The remnant of the shock wave is the blue, very hot electrons on the outside there. So there's a lot going on in that picture. In the Crab Nebula, the neutron star is a little bit more active, a little bit more dramatic. It's called a pulsar because it's launching a jet and spinning very rapidly, and you can see it in the purple nebula you've got there. We're doing questions at the end. No, for real, because I'm on the timer, and it's like clockwork. Now, these pictures are real. That purple stuff is taken in the X-ray, the same stuff used to see your bones by doctors. It's just that they're so large on the sky, and the telescopes are so powerful that you can get a lot of detail. Now, those are neutron stars, but for black holes, it's the same concept. It's just that if the core of the star that's collapsing is too heavy, remember our neutron stars between 1 and 3-ish times the mass of the sun. If you go above that, the neutron star collapses, and then you get a black hole instead. And that can actually kill the supernova entirely, or give you something a little bit more exotic, which we don't have time to go into. So both the neutron stars and the black holes are corpses of massive stars. That's all you need to remember. If I lost you earlier in the talk, welcome back. That's all you need to know for now. But this can't be the end, right? Because I've only been talking for about 20 minutes. And I promised you neutron stars and black hole mergers. So we need more. But thankfully, the universe is very generous. And most massive stars are born with siblings. They're either born in binary systems or triple systems or quadruple systems. Even when you have 3 stars next to each other, you'll have a binary somewhere in there, because otherwise it's chaos and the system doesn't survive. So we're going to focus on the binaries for now, because those concepts kind of follow through in higher orders as well. Now, binary systems are really cool, because these stars can actually interact with each other, particularly when you get to that last 10% of their lives. Because not only does the core get crazy, lacking hydrogen and everything, but the other side gets crazy as well. The star expands and contracts and expands again. There's a lot going on. And if your star expands too much, gets too big, it can actually start pouring material into its friend right there. And it's easy to understand if we go back to our picture of gravity and the funnels that are next to each other. Because those funnels, I'm going to do that with a mouse as well. Those funnels, if they're very close to each other, form a little saddle in the middle, a saddle point. So if that star expands massively, it's going to go too far that way and starts pouring into its friend. In fact, this star can expand so much that it can completely engulf its friend. And you're going to see it here go whoop, completely engulf its friend. The friend comes a little closer, and then the star contracts again. Those radii, those sizes of the 2 stars, and the separation between the 2 stars are to scale. These are state-of-the-art models from the University of Auckland, from our codes. So that's real. Well, real from the theorist's point of view. And I'm sure that some of you might be like, well, but that's just a model. What happens in real life? Well, I've got real pictures, a real GIF of mass transfer between 2 stars observed over the course of 13 days. This is bit on Iris, a very well-known what we call contact binary, because this star, keeps moving, the very bright one, you can see there's a stream of material coming in and out of you between the 2 stars, because it's pouring its outer envelopes into its friend. So all of that stuff is super important. Now, both of the stars in our binary system can be massive stars and therefore have the potential to give us neutron stars or black holes, which is great because we want these to kiss at the end. But they both have to go through supernovae in order to get there. And supernovae are no trifling matters. They are extremely powerful events, very powerful explosions. They can release as much energy in one event as the sun will in its entire 10 billion year lifetime. They can accelerate the outer layers of the star to speeds of 10,000 kilometers per second. That's not the largest number I could find. That's an average supernova on a Tuesday afternoon, by the way. I've worked on things that go as fast as 30,000 to 35,000 kilometers per second. So very, very, very fast. And therefore, they can actually kick the neutron star, the black hole. They can give it a kick and change the system itself. They can get the 2 parents closer together. They can get them further away together. They can completely disrupt the system and make that binary star 2 single stars that are just flying across the galaxy in 2 different directions. But if you can survive both supernovae, then you will end up with a binary neutron star or binary black hole system. And then what? How do you go from 2 neutron stars, 2 black holes rotating around each other to them actually merging? Well, once more, we need to go back to our little picture of gravity. It's like there's continuity in this talk. It's like I thought about it. We're going to go back to the funnels that are a little too close together. Because what we've not mentioned, we mentioned the saddle point in between the 2 stars, but we didn't mention the opening. So the opening of that funnel is round when there's an isolated object, and when there's 2 next to each other, the opening is more like peanut shaped. So as they spin around each other, they're actually going to start stirring the fabric of space-time. And we can see this with a really nice video, a really nice visualization We're going to see it in slow motion very soon. So the wheels are the black holes. The fabric, the orange fabric, is the fabric of space-time. And the drill is just creating the orbit. And you'll see these waves actually going outwards, being created by those two wheels, and then propagating out towards the edge of the fabric. And they're only stopped by the fact that the fabric is limited, but they just keep going. So in this visualization, we've got a nice wave, and a wave doesn't happen on its own. It's created by something. It requires energy. In the case of our little video, the energy comes from the drill, and in the case of black holes, it comes from the orbit. So in the case of the drill, the energy is being taken away from the battery or from the cord, where if it's plugged into the wall. The electricity is being drained from the battery of the drill and used to accelerate the wheels. In the case of the black holes, the energy is being taken away from the actual orbital motion, which, again, what does that mean? What does it mean to take energy away from a system that's orbiting? Well, it means that as they spin around each other, they're going to come closer and closer and closer together until they merge. That's how we're going to get our crazy neutron star and black hole mergers. Now, because those waves just ripple out, they're going to encounter Earth at some point. And they're actually going to start wobbling us. I know a little bit of wobble. Yes, wobble. No, I don't want to say panic. It's going to wobble the Earth. Not quite to that extent, but it will actually impact our location in the fabric of space-time, which means we have a shot at detecting these waves and actually hearing the merger happen. So how do we do that? How do we detect disturbances in the fabric of space-time? Well, there's a lot of maths involved, a lot of physics, a lot of engineering, 40 years of advances, but I promise you there will be not a single equation. We're going to only talk about the concepts, and we're going to boil it down to two key factors. We're going to need two things. We're going to need lasers and special mirrors. I'm going to be very sad when I go back to Europe and I can't use laser Kiwi in my talks anymore. They're going to be very confused. So, our mirrors are very special because they are the same distance apart from each other at a 90-degree angle. Same distance apart. And they are free to move, yet completely isolated from every motion on Earth, as well as possible. So a lorry driving past 2 kilometers away, a crow banging on a nearby pipe, none of that can even wobble our mirrors a little bit, because we only want our mirrors to move when the gravitational wave comes through, when it comes past the Earth. That's what we're trying to detect. So how are we going to see if one of our mirrors has moved? Well, that's where the laser comes in. Lasers are a very special kind of light. You can see this one, it's very green. Lasers are very special because they're essentially one color, or very close. What that means is that since light is a wave, the peaks, the troughs of that particular light wave always in the same spot. Peaks and troughs, always in the same spot. So as you shoot your laser out and split it into two to go towards the mirrors, there it gets split, goes towards that mirror, bounces back, split, goes towards that mirror, bounces back, and then reunites here before it goes to the detector. When the laser reunites, if the mirrors have not moved, the peaks and the troughs are in the exact same spot, and all is well. But if the mirror has moved, then the peaks and the troughs move as well. And you get some really weird things happening called interference. So it can be a whole course in physics that, because there's so much to do with interferences. And these detectors are actually called interferometers for that reason. So that's what you're detecting. Now, it's a very delicate instrument that's trying to make very tiny measurements. And I'll give you a number in a minute. And for that reason, that instrument is quite large. In America, the LIGO detectors, each branches are 2 kilometers across. This one, the mirror is not even visible. It's somewhere over there. It's not even in the picture. And the mirrors are also quite, heavy-duty mirrors. They're on a really big pendulum that's over 100 kilograms. The mirror is the thing at the bottom there. I think you'll see the back of it. Very complex pieces of engineering. And the reason you have to have such complex engineering, and it took decades to actually detect those gravitational waves, is because the wobble you're trying to see in the mirror, the actual displacement, is of order 0.000000000000000000000000001. I actually did them all. 10 to the minus 21 meters, which is 1,000 times smaller than the atomic nucleus, which itself is 1,000 times smaller than the atom. So we're looking at orders of magnitude, many orders of magnitude, 6 orders of magnitude smaller than the building blocks of the matter around us. Now, there's a quote, which I can't remember verbatim, that says something along the lines of, technology, if sufficiently advanced, is indistinguishable from magic. That's the way I feel about gravitational wave detectors. Because it's slightly outside my field. I use their results, but I don't actually work doing that kind of detection. So it's absolutely stupendous that they've managed to actually detect these. But they have. We did detect gravitational waves. The first ones, well, directly, I should say, because we had evidence in the 60s. But the first direct detection of gravitational waves was back in 2015, in the before times, when the UK was still part of Europe. Before Trump became president, and when having corona was a good thing. So back in 2015, we detected the first direct observation of a gravitational wave. It has a lovely name, GW15 and 914. These phone numbers are actually date. GW for gravitational wave, 2015, September 14. Very simple. And this is what it looked like. There are 2 panels on here. We're only going to look at the left one because it's easier, and I'm going to use the mouse again to make sure the online folks can actually follow. So we've got the gravitational wave here. That's the observation. Time is on this axis. It's the same for all of the panels, and you can see it's a tiny value in seconds, right? We're looking at tenths of seconds, and you can see the wave goes up in strength massively, and the peaks come closer and closer together over time. That is the frequency increasing. The peaks coming closer together, that's this. That's the frequency going whoop, like a chirp, whoop, like that. That's a marker of 2 black holes merging together, or 2 neutron stars merging together. The merger happens right here, right when that wave starts dying. Now, what's really cool there is that you can see the observation match the theory quite nicely. And what's very convenient, if your theory and your observation work together, is that you can use the theory to derive interesting properties from your observations. In this case, you can actually figure out how massive the black holes were, which is neat. So in this event, we have a 35 solar mass black hole merged with a 30 solar mass black hole to make a 62 solar mass absolute beast of a black hole. And I ruined the surprise by going through my slides a little too quickly. But you might notice that 35 plus 30 do not equal to 62. There's sort of 3 missing somewhere. And those 3 solar masses, or 3 solar masses worth of matter that were turned into energy when the black holes collided. And that created the gravitational waves. Well, the energy was taken from the orbit as well, but that went out into space, into gravitational waves as well. So pretty staggering, not gonna lie. When I first heard about it, I was a young PhD student when this happened, and we had to talk by one of the LIGO people. I was like, where did the 3 solar masses go? And the guy was like, in the gravitational waves, as if it was obvious, and I was an idiot for thinking that 3 solar masses worth of matter disappearing into energy was just, oh, no, casual, like, of course, like, yeah, why not? So yeah, when that happened, it was the most energetic event in the universe at that particular point in time. So no traveling matters, once again. Now, since then, we've seen quite a few black holes merge. In fact, gravitational waves is one of the main ways that we can study black holes and their masses nowadays. This plot is very nice, very simple. It's got only one axis. the y-axis, we've got mass. 1 solar mass here, 200 solar masses there. The shapes are arranged so that it looks pretty and symmetrical, sort of. Now, the colors tell you what kind of object you're looking at and how it was found. The blue stuff is the black holes that were found using gravitational waves when they merged. The red stuff is black holes that were found using traditional telescopes, using light. Now, it's a little bit harder to find something that is black using a traditional telescope. And then gravitational waves completely dominate this plot. Right? They completely take it over since 2015. There's two other colors on that plot. The neutron stars are in orange and in yellow. The yellow neutron stars are the ones we know of from typical telescopes, and there's a handful of orange ones from gravitational waves. Now, there's only a handful of those because obviously gravitational waves from things that are less massive, they're less strong, the wobble is smaller, even harder to detect. But we've seen a handful of those. And the first detection of a binary neutron star merger was actually the most impressive event. So that's the one I'm going to talk to you about today. And it's called 170817. And it is my favorite explosion in the whole universe at this particular point in time. Now, 170817 happened in 2017, August 17, right? And I'm not going to show you the gravitational waves. You've seen one of those before. But I'm just going to tell you what masses were derived from it, a range for the two neutron stars. You couldn't figure out exactly what neutron star 1 was and what neutron star 2 was because it's a little too messy at those range. But you can tell the mass of a black hole, which is neat. Now, because the two objects that came together are neutron stars, they're shiny, they're bright, which means that these mergers are a little bit more dramatic than the black hole mergers, which is also why they're my favorite. And to understand why they're a little bit more dramatic, we're going to use a simulation. We're going to have a look at a video that shows you two neutron stars merging together in slow motion. So don't worry too much about the color, it's probably density. And you'll see that as these neutron stars are coming together, because they're spinning around each other, they're not going to collide head-on. They're going to spiral into each other and then eject a whole bunch of matter outwards into space. They also create this little donut, this torus in the middle around the hypermassive neutron star. That's going to launch eject. And that neutron star, that big yellow neutron star, is too massive, so it's going to collapse down to a black hole as soon as it releases too much of its rotation. So we've got three things that are going to happen in our binary neutron star merger. Three essential markers we have a hope to detect. So gravitational waves are the first one, and we've talked about this already. The short gamma ray burst, you don't need to remember the name, but that's just what it is the jet that is launched a few seconds after the merger, when you've got that donut, that torus, that red donut we were seeing in the picture. And kilonovae, which are the shiny thing that comes afterwards from the rest of the material that was ejected in the merger. Now, these kilonovae are essential for life as we know it. You might never have heard of kilonova. You've probably heard of supernovae, maybe at some point. Kilonovae are different because it's a different mechanism. They have a similar name because they shine for a similar reason. They're very radioactive. And the reason they're very radioactive is because they create a whole bunch of new elements. In this case, they create things like gold, like platinum, palladium, like rare earth elements that we need for our technology, that are essential for things like our phones. And truth be told, we don't fully agree on where all of these elements are created. Some people argue that binary neutron star mergers are the dominant source of these elements. Some people say, no, it's some other really crazy rare mechanism, and they'll fight it off at a conference, they'll be fine. That's why I still have a job, it's brilliant. But they are essential to life as we know it. Now, in the case of 170817, we have seen all three of these markers. We saw the gravitational wave. You can see the chirp going whoop, in like a Hanford, whoop, in like a Livingston, and nothing in Virgo. Virgo is another gravitational wave detector that was in Italy. It's still in Italy, but it was on at the time. But it didn't see anything, despite the fact that it was on. That's because the merger happened in its blind spot, which was actually very useful because gravitational waves are very difficult to pinpoint in the night sky. In the past, the sort of areas that we had to search for, I mean, those are actually black hole mergers. You wouldn't search for anything because they're dark anyway. But the sort of areas of origin are these big bananas. We actually call them bananas. So see the red stuff on both sides of the sphere of the sky? Massive areas. For 1708-17, it's tiny, which means we can actually search this area of the sky. We actually have a hope to find the other markers. And people found them. They found the gamma ray burst. You can see that peak just after the end of the chirp, so that's the merger. And then there's the peak. The gamma ray burst happens less than 2 seconds after the merger. It's enough time to make that donut that launched the jets. It doesn't last very long, less than 2 seconds, but powerful enough, you can see it. The other thing we found was the kilonova, the actual, optical light from the merger. You can see it in this GIF. Oh, back to the mouse. You can see it here in its galaxy, in its host galaxy, nice and big, very easy to take a picture of. Then you've got a close-up here, August 22nd, August 26th, August 28th. You can see how quickly it is fading. That's why we are kind of in a bit of a race on the clock when we're trying to find these other markers of binary neutron stars, and we have big areas of the sky to search because they fade quickly. This one peaks, the light peaks within 1 or 2 days. Each notch is a day, within a couple days, and then it fades very quickly. A typical supernova will peak around there. So it will have a rise and then decay much slower. So you're looking at a factor of 10 faster. Very difficult to spot, but we got it. And we got it, and we got the galaxy that it was in, and that's brilliant because if you give me a galaxy, I can tell you the age and the chemical composition of the stars in that galaxy, which tells me the age and the chemical composition of the system that gave birth to that big explosion, which is cool because we don't know exactly where they come from. It was the first one that we saw. You will indulge me, hopefully, in the next few minutes, because I'm going to show you my very own squiggles. That took me 2 years, so take a good look at it. That's what I did at the University of Auckland. The reason it looks a little bit more complicated than the rest is that it is publication ready, so don't worry if there's words on it you don't understand. It's because I should have simplified it, and I just didn't. I'm going to walk you through it. So these are my squiggles, and the gray squiggle is the light from just around the explosion. So this bit, just around there, you take all of that light and you split it across all of its colors. Blue is over here, red is over there. And the reason this is very squiggly indeed, and it's very meaningful, is because that light contains all of the light from all of the stars in that little patch of sky. You can't see the individual stars because it's 120 million light years away. It's a little tricky, but you can still see their lights. It's just blurred together. And using our state-of-the-art models, I can use the blurred light and then make a combination of stars with the models to make fake blurred light and then match it to figure out which stars I need to mix together in order to get the right squiggles in the right space. And when I do that, I figure out that this galaxy has two main types of stars. There's been two main events of star formation, we say, right? The main one is 95% of the mass of the galaxy. It's all stars, they're metal poor. Remember, metal in astronomy, anything that's not hydrogen or helium, right? So they're a little different from the sun. They're between 3 and 10 billion years old. They're about half the chemical composition of the sun in terms of metals. The young ones, very different. The sun is about 5 billion years old, by the way. These ones are like a fifth of that, and they have a lot more metals. Now, this is neat, a little boring, but it's neat because using that information and the mass that I was given by the gravitational waves for the neutron stars, I can go back to my models and be like, okay, I look at all of my models and I look at the full genealogy from birth to death. Which ones can give me that event? Which ones can actually give me that event at the right time so that we see it on the date, well, around the time that we saw it, right? So not 5 billion years ago, not 10 billion years from now, now. So I rewound the tape and I found something like this, which is once again publication ready. So there's a lot of really weird things happening there. Case BCE, don't worry, you don't need to know what this is. This is for the referee. Just follow the colors and follow my voice. I'm going to tell you the story of 170817. This is the first time that we've been able to rewind the tape on an event like that, to take a snapshot in time, one explosion, one death, and try and figure out the full genealogy of a star from its birth. So this one, very likely, was born about 7, 8 billion years ago. It was a binary system with the first star had 15 times the mass of the sun, the other star had 12 times the mass of the sun, so less massive, but not quite half, right? And the first star spent 90% of its life doing a bunch of nothing when it was burning hydrogen into helium in its core, right? Then, when it ran out of hydrogen, it went really big, expanded, engulfed its friend, and that's what we've got here, common envelope. Later on, it did it again. It expanded once more, well, half the time. It's an optional step, this one. You can skip it if you want. And poured more material into its friend when it was just about to die. It exploded as a supernova, left behind a neutron star. Then you have a neutron star and a star next to each other. And that 12 solar mass star is going to start dying. It does it after the bigger one because that's how stars work. The more massive ones die faster. And it's going to go through a very similar process, expand, engulf its friend, potentially go through an extra mass transfer event, explode as a supernova, and then you'll have your binary neutron star system. And after a few billion years, kaboom, gravitational wave, we detect it, we see it. All right, so last thing to note about these binary neutron star mergers is this is the first and the only one for which we have all 3 markers, which is good because that means I still have a job. That is what my proposal is about, if I get the money, because it's the first time we've been able to do that kind of work, but we need a lot more in order to figure out exactly what's going on with these objects and to actually understand them and understand where all of the cool elements that we need that they're making actually come from and answer some of these fundamental questions that we have. So in the last 3 minutes, we're going to wind down. We're going to talk about very briefly about black hole neutron star mergers, and I'm going to end on a video because that's easy, right? Black hole neutron star mergers, that's the missing thing that I've not talked about yet. We talked about black holes, neutron stars. Of course, you can have a black hole and a neutron star next to each other, and they can merge. Now, if your neutron star and your black hole have similar masses, the neutron star is going to get all shredded before it gets eaten by the black hole, and you're going to get a weird thing like that. That's an artist's impression in that picture. But in the case of these 2 detections that happened in January 2020, the black hole is much larger. Because it's much larger than the neutron star, the merger is going to look something like this. This is a very nice visualization made by our nice friends at OSGRAV, our Australian gravitational wave specialists. You can see the gravitational wave because it is disturbing the light in the background. And you can see as they're spinning faster and faster, the gravitational wave frequency increases. The neutron star becomes tear-shaped and eventually gets swallowed by the black hole. Neat, isn't it? Do we want to see it again? Let's see it again. Yeah, neutron star get eaten. The distortion of the light isn't just a trick to help you see the gravitational wave. It would do that because light follows the fabric of space-time, so it would get all messed up like that. And this beam, and you can see it's still wobbling a little bit for a while. And that's called the ring down. And it does happen. You can see it in the gravitational wave. It's actually this little part. See, that's a merger beam, and then those little drags that's ring down. It's based on that's proper physics. Right. So I'm about to thank you for listening to my talk. Before I do, I need to thank my colleagues because they're amazing, and my boss Jan at the University of Auckland. She's been a fantastic mentor. I also want to thank the organizers of the Beatrice Hill Tinsley talk, because this is the very last talk, and it's gone very well over the past month. I visited like 10 different places and given this talk about 10 times, and it's been a success every time because they organize it so well and so smoothly. So thank you so much for hosting me, and thanks to all of you for coming and listening. Questions, indeed. Yes.
Heloise, how do we know where to look for optical confidence event? What role does that play in the analysis of the whole thing? How much importance is the optical vis-a-vis LIGO and stuff like that?
Yeah, so how important is it to see the actual light that you typically see with a telescope in these mergers? How important is it to the analysis compared to just getting the gravitational wave? For black hole neutrons, for binary neutron star mergers, it's really, really important, especially for people like me. So I can technically try a similar analysis with just the masses from the gravitational wave, but honestly, the answer will be so muddy. There will be so many different possibilities that it's not actually going to be helpful. Even for this particular one, where we have a very good location for the galaxy and excellent data, the story I gave you is the most likely story, but not the only possibility. It's very often the case for things like that, and that's why we like to have more than one, right? Because if you see loads and loads and loads of different objects, you can put all of these probabilities together and get an even better idea of what's going on. So for every single object, if you get the optical light and you get not just the optical light, but if you get the galaxy, what's key is getting the galaxy, people like me. But even if you don't, you can still do some of that work. It's just a lot less constrained. But at the end of the day, when you pull all of your information together, it's still going to play a bit of a role. Thanks very much for your question. Do you have a question?
Oh, just further on to that, do they arrive at the same time? The gravitational wave and the light?
So pretty much, the gravitational wave arrives first because it is generated just before the merger and as the merger happens. So gravitational wave arrives first. Then you have your merger. You have the torus that creates the jet. The jet happens about 2 seconds after the merger, maybe a bit less. And then you're going to start seeing the light from the rest of the material that was exploded. And the speed at which you see that light depends on the color of the light you're looking at. See, it didn't peak at the same time. And it's all because of something called opacity. Opacity is a beautiful thing. It's basically how transparent the material is to a certain type of light. Different types of light, the material is different, it's transparent in different ways. So red light peaks at a later time, and blue light peaks at an earlier time. So it depends on what you're looking at exactly. Oh, sorry, we're going to go around, and then if you've got more questions, we can go back to you. Yeah, question?
Hi, I've got a question about the state of the matter of the neutron star when it is about to enter or merge with the black hole. Because neutron stars they're not ordinary matter, like all the space is squashed together as atoms. So when you showed that last picture, where you said there's like this misty thread, what do I imagine there?
Yeah, that's a very good point. So neutron stars are a different kind of matter. They're not normal matter like the stuff around you. So how does that work when it's actually coming into the black hole? The reason I'm repeating answers, by the way, is because some people will not have heard. It's not because I'm not listening, and some people on the live might not hear the question. So just FYI. So neutron stars, they are a different kind of weird, very, very weird kind of matter. They're called degenerate matter. It's like the fifth phase of matter, if you will. And And the reason they're weird is because the particles are squished together as tightly as they can be. In a typical atom, there's a lot of empty space. There's a whole load of nothing. The atomic nucleus is 1,000 times smaller than the atom, and it's in the middle. And everything else is a cloud of electrons. All of that is gone in the neutron star. It's just basically the same density as an atomic nucleus, extremely, extremely dense. So how does that react to merging with black holes? Well, the nitty-gritty will be particle physics and general relativity. But what's very interesting is that, especially as they're being scattered, as some of the material of the neutron star is being scattered, what happens to those neutrons? Because neutrons, if you're not familiar, they can't really survive on their own. You can't have just two neutrons hanging out, hugging each other. There needs to be a proton. And if that's not the case, one of those neutrons is going to turn into a proton real quick, because they don't like to be without protons. And so what happens when your neutron star gets a little shredded before it gets into the black hole is that droplets of neutrons are going to go flying into space, and I'll be like, hold on, it's not nearly as dense as it used to be. I can finally turn into a proton, woo! And we're going to get something called beta decay if you want to look into it. And so these are going to form seed nuclei that then can be shot out by more neutrons and create some of these really heavy things like gold, platinum, palladium, etc. So the way that the neutrons react when they're in such a strong gravitational field that it tears them apart, literally, is very interesting, because that's where we get some of these rare elements that you can't get anywhere else. So I hope that answers your question.
Where do the electrons come from, sorry?
Oh, the electrons. From when you make the neutron star, or?
Well, you were saying that in this stage, when the neutron star gets, I don't know, spaghettified or shredded, that material is going in. There are some neutrons that are floating about as those bubbles. They turn from neutron to proton.
Yeah. Oh, they release. They release an electron. So a neutron becomes a proton by releasing an electron and a neutrino, an electron neutrino. That's called beta decay. So if you want to look into it, that's how particles turn into other particles. Woo! So that's what. Yes.
So like a star dying into like neutron stars, like a literal of the star. How does life?
How does the life of a neutron star end? That's such a good question. So if it doesn't merge like this, it just cools down and becomes dark eventually, and that's it. Which is pretty boring, I'm sorry, but that's what happens. It takes them forever though to cool down. But if the neutron stars are next to another star that's not dead yet, so like not a neutron star or black hole, a typical star, and there is mass transfer, actually. Haha, my picture. Beep. Beep. Things like that, where one star pours material onto a neutron star, can make the neutron star really interesting, because it can spin it up, it can make a disk around it, it can launch some jets, it can get crazy. So it can have a fun life after the star dies. But then the neutron star itself is not really going to die in a dramatic manner unless it goes through a merger like we saw today. It's just going to slowly cool down over billions and trillions. Aces? Yeah.
I've just got a question. Gravitational waves, when they're really intense and in close proximity to one of these events, and presumably there's matter in proximity as well. Is there any mechanism by which the gravitational wave can dump energy into the matter? Or does it just pass through without having...
Oh, can the gravitational waves actually give energy to the matter? So they just kind of make you move. So I guess to an extent they give you kinetic energy. But the actual transfer of energy from a gravitational wave to matter is the matter of general relativity. But they because they're really faint, quote unquote, they don't make your mirrors move by much, right? It's not a significant amount at all.
Yeah, I was sort of thinking more in the immediate surrounds.
Oh, yeah, that's why you, the fact that they can stretch your neutron star and make them, and like shred them, is a good way to see their effect, really. Because they have the power to shred some of the second densest object in the universe. They can shred it and eject, like that material that gets scattered in the binary neutron star merger moves at speeds of like 10% of the speed of light, 20% of the speed of light. Really, 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 really fast. So it's a lot faster than, like 10 times faster than the typical supernova. So very extreme events. Do we have questions from the chat?
We do have questions from the chat.
Woo-hoo!
So, 2 questions from Mitchell. His first one is, regarding your models, considering the old stars are metal poor, does that mean they are low mass? Because if they were high mass, they wouldn't live that long, and vice versa for the young.
That's a very good question, and no, it doesn't. So what I mean by metal poor is metal poor at birth. So stars are born from a cloud that has a given amount of, hydrogen, helium, and other things. And the stuff you see on the outside of the star, the amount of metals on the atmosphere of the star, the outside of the star, which is where the light comes from, that gives me the squiggles, that is basically fixed by what they were born with, because the new metals they make are concentrated in the middle of the star, in the core of the star. That's where they are. It's very stratified. Like you said earlier, that stars have layers, and yeah, those massive stars have layers when they're about to burst. So yeah, it's their initial cloud that is metal poor, regardless of how many metals they've made in their core. But yeah, very, very good clarification to make. What's the other question?
Mitchell's second question was that he wants to know what font you use because he likes it a lot.
I have no idea. We can figure it out together. Someone else had a second question. I feel bad for.
No, there are some other real questions. While you're finding the font, I'll ask you.
Maven Pro, woohoo! And this one is another graphic I made, so you won't know. And this one is also Maven Pro. So Maven Pro all the way.
Right.
What are the other questions?
So the other questions. Joseph wants to know, where are the population 3 stars?
At the very beginning of the universe, definitely not here, because population 3 stars, for everyone who doesn't know, there's 3 kinds of populations. We're not going to talk about 1 and 2. Whoop! It's a very archaic way to talk about stars, like from the mid-20th century. Once again, population 3 are the first ever stars to be created in the universe. If you didn't know that the sun was not created in the early universe and that it had, parents and cousins that were born before, surprise. The sun is about the 3rd generation star, something like that. The first stars created in the universe have no metals whatsoever, because hydrogen and helium are the things that were made in the Big Bang. A little bit of lithium, nothing else. Everything else was made by stars. So the first stars created in the universe didn't have metals. And metals, although they make only a few percent to fractions of percents of the mass of stars, are essential to the good going of their lives as we understand it in the things I've shown you. So them expanding a lot, losing mass, all of that stuff, that's driven partially by metals and how they react in the stuff. So we're not going to go into details. But those stars are therefore very, very different, and they're a lot more massive, like 1,000 times the mass of the sun, potentially. So they're very weird, and they die very quickly. The more massive the star, the quicker it dies, the quicker it goes through its fuel, the quicker it gets out of the way. So that galaxy, with things that are born maybe like 10 billion years ago, is kind of the upper-ish limit for those stars to be born. That's still like 3 billion years after the Big Bang. 3 to 4 billion years after the Big Bang. So the population 3 stars would have already exploded and enriched the universe by the time these stars were created and that galaxy was born as it is. Any other questions from the chat?
Final one from the chat. This is from Mike, and he wants to know, if 2 black holes merge, does the smaller mass one fall into the event horizon of the larger one, or does the event horizons just merge and they both effectively fall into the combined one?
I think it depends on their mass ratio, so the difference between their masses. If they're similar masses, it's probably a weird merger of the event horizons. If one is much bigger than the other, the smaller one probably just drops into it. But I'd have to look at the actual mass of the general relativity, and it's complicated. But yeah, good question. Who had a second question in the audience, and I shut them down?
Oh,
Go on.
Well, just the supernova you showed us, your favourite one.
Yeah.
What sort of size is there?
I can't remember. Really big.
Hundreds of light years.
Oh, I used to know that, but I cannot remember that on top of my head. So if someone can Google how large Cassiopeia is in light years. No one's Googling it? Anyone? It's on Wikipedia. Yeah, I can't remember on top of my head. And do not be fooled. The fact that this dot is this diameter does not mean that this is 10 kilometers. It's only this diameter because it's a point source, and that's how big it looks in the telescope. It's very shiny and very bright, but it doesn't actually tell you the diameter of that thing. It's basically a dot in the image. All right. Any last questions? One last question from the audience? No? Too scared? Too tired? Me too. Same. All right. Well, thanks very much.
And
Back to you, Bill.
it's traditional for the society to present a small gift of
I love
a
gifts.
thanks, and also to remember us by your travels back to Europe.
I'm showing it to the YouTube people. I've not had that before. I've not been given Greenstone by anybody in New Zealand, so this is my first. So this actually means a lot. Thank you very much. That really means a lot. Thank you so much.
Thanks very much.